everyone. Today we're doing notes for 6.6, normal approximations to binomial distributions and to the p-hat distribution. Normal approximation for the binomial distribution. It's most useful when finding the probability that the range of successes is in a given range. A normal distribution can be used to approximate the probability of r successes out of n binomial trials. In order to use the normal approximation, the products n times p and n times q, or n times 1 minus p, must both exceed 5, where n is the number of binomial trials, p is the probability of success on a single trial, and q is equal to 1 minus p. Unless n is fairly large, a continuity correction may be necessary in order to improve the approximation. So we consider a binomial distribution where n equals the number of trials, r equals the number of successes, p equals the probability of success on a single trial, q is equal to 1 minus p, the probability of failure on a single trial. So if n times p is greater than 5, n times q is greater than 5. So again, I'm going to write this larger. Our n times p is greater than 5, and our n times 1 minus p, which is q, is greater than 5. We have to have both of these true. Then R has a binomial distribution that is approximated by a normal distribution with mu is equal to n times p. Again, I'm just going to make these larger so we can see them later. And our sigma equals the square root of n times p times q. Or in other words, our sigma is equal to square root of n times p times 1 minus p. Note, as n increases, the approximation gets better. All right, so we're going to consider a binomial experiment with n is equal to 20 trials, and our p is equal to 0.45 probability of success. Using the binomial distribution to find the probability of exactly 10 successes, so that means our r equals 10. This is our binomial PDF, 20, 0.45, 10. Again, we put our n, then our p, then our r. So our calculator gives us this 0.1593. And again, this is our binomial. Calculation. So to use the normal distribution to approximate the probability of exactly 10 successes, our normal distribution we use has a mean of n times p, which is 20 times 0.45, which gives us 9. So again, our mu is 9. And then we have our standard deviation, sigma is 20 times 0.45 times 0.55, the square root of that, which gives us 2.2249. So this is our sigma. So if x is a random variable with this normal distribution, then the probability x equals 9 is 0 because x is a continuous random variable. It can take on any numerical value, but the binomial is discrete. It can take on only whole number values. To account for this, we find the probability that x falls between 9.5 and 10.5 because these would be the class boundaries on a histogram which correspond to the class 10. So we find the probability that it's between 9.5 and 10.5. So another way, this is using the z-score. If we wanted to do it using normal CDF, we do normal CDF of 9.5 to 10.5. Our mean is 9. Standard deviation is 2.2249. And this is going to give us 0.1610. Okay, and again, this is our normal approximation. So the difference between these answers, if we actually subtract them, we get 0.0017. So while the normal approximation is not perfect, it has estimated the probability quite accurately. So the graph to the right here displays the probability histogram for the binomial distribution with n equals 20 and p equals 0.45. So if we're looking at this picture, the binomial, oh my gosh, this is the histogram, okay? And it also gives the normal bell curve with the mean of 9 and standard deviation 2.2249. So again, the normal distribution is the curve. As you can see, the bell curve follows the histogram very closely. The computation we just did found the area under the bell curve between 9.5 and 10.5. So if we see here, we see 10, so right here, this is 9.5. Right here, this is 10.5. So we're specifically looking at this bar of the histogram, okay? And so we're doing the computation of finding the area under the curve from these parts. So that is going to be, the curve goes like that. And so you can see that it's very closely will estimate what we're looking for. All right, so the owner of a new apartment building must install 25 water heaters. From past experience in other apartment buildings, she knows that Quick Hot is a good brand. A Quick Hot heater is guaranteed for 5 years only, but from the owner's past experience, she knows that the probability it will last 10 years is 0.25. So this 0.25, that's going to represent our P. And if she's installing 25 water heaters, that represents our N. What is the probability that 8 or more of the 25 water heaters will last 10 years? Define success to mean a water heater that lasts at least 10 years. So we want 8 or more is what we're looking for here. Okay, so a good normal approximation, N times P has to be greater than 5, N times Q has to be greater than 5. So let's check this out first. So our N times P, that's 25 times 0.25, which is 6.25, which is greater than 5, okay? Then we have to check N times our Q, which is 1 minus P, so this is 25 times 0.75, which gives us 18.75, which is also greater than 5. Okay, so we can use the normal approximation. So remember, we want the probability 8 or more. Okay, so the probability that R is greater than or equal to 8, that's what it looks like for a binomial. So we need to figure out what this looks like for the normal approximation. So we're looking, here's my bar where 8 occurs. Oops. And so right here, x equals 7.5, that's the lower bound of the class that holds 8. Okay, so we're going to look for the probability that x is greater than or equal to 7.5 when we use the normal approximation. So we need to make sure we have, this is going to be our lower bound is a 7.5. Our upper bound, we can use our 10,000 because we want just greater than or equal to 7.5. We need to find our mean and standard deviation. Okay, so these are listed on the side, but I'm going to go through calculating them. The mean is N times P. So we already did that above. This is 6.25. Our standard deviation is the square root of N times P times 1 minus P. So this is square root of, we have 25 times 0.25 times 0.75. And that's going to give us 2.165. All right, so I want you to do the normal calculation to figure out the probability. Okay, so we have normal CDF Lower bound is 7.5, upper bound is 10,000. Our mean is 6.25, standard deviation is 2.165, and so that will give us 0.2818. B says, how does this result compare with the result we can obtain by using the formula for the binomial probability distribution with n equals 25 and p equals 0.25? So now, remember, we're doing the probability that r is greater than or equal to 8. If you recall, when using the binomial distribution, we have to do this as 1 minus the probability that r is less than or equal to 7, because the binomial calculation only does your value and below for cumulative. Please find this one. Okay, we can do 1 minus binomial CDF. And then we have 25.257. And this gives us 0.2735. All right, so now how do the results of part A and B compare? So part A, this was our normal approximation. That was 0.2818 minus part B, this was our binomial calculation. So 0.2735. If I find the difference, we get 0.0083. And this is very close. Okay, again, in the beginning we showed our n times p was greater than 5 and our n times 1 minus p was greater than 5. So we know the normal approximation should be close to the binomial. Okay, sampling distributions for proportions. Suppose we conduct a binomial experiment with n trials, but instead of recording the number r of successes, we instead record the proportion of successes r divided by n. This proportion is a random variable called p hat because the proportion of successes is an estimate for the probability of success p. The distribution of p hat can be approximated with a normal distribution as long as n times p is greater than 5 and n times q or n times 1 minus p is greater than 5. The same criteria as above. I'll rewrite that one with 1 minus p. And the mean and standard deviation are mu is equal to p. So we would say our mu of p hat is equal to p. And our sigma is equal to the square root of p times 1 minus p divided by n. So again, our sigma of p hat is equal to square root of p times 1 minus p divided by n. N is our number of binomial trials, the fixed constant. R is the number of successes. P is the probability of success on each trial. And Q is equal to 1 minus p, the probability of failure on each trial. So p hat, our sampling distribution tells us for here we have our n times p is greater than 5 and our n times 1 minus p is greater than 5. Again, just writing these larger so they stand out. The p hat distribution is approximately normal. The mean of the resulting p hat distribution is p. So again, our mu or our p hat is going to be equal to p. Standard deviation, also known as the standard error, is the square root of p times q divided by n. So again, our sigma of p hat is equal to square root of p times 1 minus p divided by n. All right, the annual crime rate in the Capitol Hill neighborhood of Denver is 111 victims per 1,000 residents. This means that 111 out of 1,000 residents have been the victim of at least one crime. For more information, you can visit that Pitton Foundation website. These crimes range from relatively minor crimes, such as stolen hubcaps or purse snatching, to major crimes, such as murder. The Arms is an apartment building in this neighborhood that has 50 year-round residents. Suppose we view each of the n equals 50 residents as a binomial trial. The random variable r, which takes on values 0, 1, 2, all the way up to 50, represents the number of victims of at least one crime in the next year. What is the population probability P that a resident in the Capitol Hill neighborhood will be the victim of a crime next year? What is the probability Q that a resident will not be a victim? All right, so we have 111 victims per 1,000 residents. So that's going to represent our P. So we have 111 divided by 1,000. So that gives us 0.111 as a decimal. And so then to get our Q, remember that's 1 minus P. We do 1 minus 0.111, which is 0.889. Consider the random variable P hat, which is equal to R divided by N, which equals R over 50, right? Because we have these N equals 50 residents. Can we approximate the P hat distribution with a normal distribution? Explain. So we have to do N times P. So our 50 times 0.111, that gives us 5.55. So that's greater than 5. That's good. We also have to check N times 1 minus P. 50 times 0.889. which gives us 44.45, which is also greater than 5. So both of these are greater than 5. So yes, you can use the approximation with the normal distribution. What are the mean and standard deviation for the P hat distribution? I want you to use our formulas from above here and find the mean and standard deviation. Okay, our mean, mu of P hat, is equal to P, so this is going to be 0.111. And our standard deviation, sigma of P hat, is going to be square root of P times 1 minus P divided by N. So this is square root of 0.111 times 0.889 divided by 50, which gives us 0.0444. And that is the end of our notes for the unit.